So a quick introduction. So I'm Bernard. I founded Game Labs. We're doing prototypes with game technology. So that means we take somebody's idea and we turn it into a playable prototype by means of programming. And that is used then to test and verify concepts as well as represent them to, for example, potential investors. So it's like an iterative approach that we take step by step, in which you iterate until you feel satisfied about all the features that you can be confident, like, okay, this concept is actually going to work. All the unknown factors have been dealt with, and you feel more secure about continuing the project. Physics is all about determining forces that are existing in a certain system, and then applying whatever the sum of those forces is to objects, and that's what makes them move. So once you determine all of the forces, and that's actually the more difficult thing, like which forces do you take into account, on which position on a certain object do you apply them. Once you calculate all of them, you can, if you know the mass, which is just a number, and you divide the force by the mass, you know the acceleration, and from there it actually starts moving. So you can, from the acceleration, you determine the change in the velocity, or the velocity itself, and then you change the position by applying the velocity multiplied by the delta time, which is in a game, it's the time between frames, basically. And that's what they call Euler integration. So it's not exact, because if you would have a fluid curve of something accelerating, it would become like little line segments where the length of the segment is the time between frames. But as long as you keep that constant, you don't have to worry, the physics are stable. It's just a matter of tweaking the mass or other values until it feels right. So the first game where I used physics was at one company in Ghent in Belgium. It was PetFat Marine Patrol. It had different titles, but I think this is a video. Yeah. So there is a boat in this game, and I'm going to explain a little bit more about how that worked. So basically, in the game, you had like an infinite water surface, which was an interesting challenge. Like, if it's infinite, how do you do it? Like, how do you simulate it? So basically, very quick. You have the camera in the game, the 3D camera, that has a view frustum, which is a shape that describes that is actually visible. It's like within this volume, everything that's not occluded by anything else is visible. So what you do is you consider an infinite plane, you intersect it with the view frustum, and that's where you need to make the water move. In this case, so water can be really complicated to do, and this had to run on the Nintendo Wii. As I mentioned, slower than the first iPhone. Like the hardcore way of doing it, or if you say, okay, I'm just going to be brutal to my processor and whatever, and then resources, I'm just going to simulate every water particle, and whatever the particle size is that you choose. So this is an example of 128 million particles simulated. It's not something I made, it's just an example. And yes. So you see the little kind of styrofoam balls, and that shows like how they're simulated, and then with some shader effects you can make it look something like this. So that gives you something pretty realistic. Of course, if you have an entire ocean and a Nintendo Wii, you're not going to be able to do that. This requires like GPU hardware. So for this game on the Wii, to make it run, so instead of actually simulating all water particles, I just said, okay, basically the water moves up and down. So you could see that as a sine wave. Of course, it moves up and down in a more, not like a super regular pattern, like it's not like the waves go like exactly like this. So you have the Fourier transformation thing or I think maybe it's a law of Fourier or whatever, but he stated that every signal can be expressed as a sum of sines. Like an infinite sum, of course, but but you can approximate it by having a limited set of sine waves. So what I did is, okay, I just added up a bunch of sine functions with different frequencies, amplitudes, phase offsets. So, and I think I needed like 5 or something, and then it looked already pretty good. And then, since we had the water plane intersected by the view frustum, we had like a grid where we could change the resolution of the grid would be lower further away, and then for the points in that grid, the sum of sine waves had to be calculated. So, and then the water moves. So actually, that's what on my slide. And yeah, go ahead.
Did you have any like formalized way that you used to determine sort of the amplitudes and the?
No, it was really like so. I said, okay, let's have an arbitrary number of sine waves depending on the variable, and then I could set the amplitude. I could set a phase offset. I could set the frequency, and then I would just play around with the numbers until it would actually run fast enough on the V, so reducing the number of sine waves, trying to find a kind of sum of sine waves that looked as good as we could within the resources that we had available. And yeah.
So you sort of did that at random?
Yeah, it's not like we had maybe a 3D capture of a moving ocean and then we tried to like mimic it to be exactly the same. No, it was really like it's a game. It's not a simulation, so it's really like we need to have something that feels nice and also that gives you a satisfying feeling when you take your boat and you're skipping the waves. So maybe you don't want the waves to be too small, so that was also a factor. So the system where we said, okay, basically the ocean was, it was simplified, like we had to take this view first and we use that to intersect the infinite water surface. And I just simplified it so it's always a square to make it easier, because a square you can divide into I mean, it's a nice way to have patches of different resolutions in square. Just simplified it a lot, because you can just do divisions by 2 and things like that. And that's what you call tessellation. It's like the 3D mesh that was generated would have a lower resolution further away from the camera. So that was also a factor in the performance. Should I turn it a little bit?
I was just about to ask a question. Is it more cost effective to do a hardware tessellation as opposed to using software to do your renders?
Well, I would assume anything done in hardware would be more effective, but there was not much available on Nintendo Wii, so it was done in the software. But the nice thing was that the access to the functions and everything. I mean, everything was pretty low level. So one of the things that was good is that if you wanted to build a mesh from scratch and send it to the GPU, like for example, if you would do it in Unity, it would mean the whole, a mesh consists of like 2 arrays. To put it really simple, like one array is all the vertices, like vector trees, like points. And then you have an array that points that lists indices, indexes in the vector array to say, okay, these are the triangles. So if you make changes in that and you change the values of the vertices because they have to move up and down, there we didn't have to copy it all the time. So it just copies it once into the memory instead of if you want to change the mesh, then it would create another copy of the array, because that usually makes a big difference when you're creating meshes at runtime. So you just see that you can skip, and now I'm going to talk a bit more about the boat and the steering. So I modeled it as an engine, and by using the analog stick on the Wii nunchuck controller, you would move the engine, and so when we're talking about forces, you can see that, okay, there's going to be a force applied at this point, exactly where the blade is. And then you since in games and 3D applications, objects are positioned at a certain pivot or origin point, you have to translate that force to that origin. And that means, again, can mean there's a rotation. Like if you have an object and you push like at the back, it will rotate in this direction, for example. So that's one of the important things. So if you have the center of your object, at which you basically move around, and you have a force here, then you have to move that force to the center. And so basically the size of the force will be the force here multiplied by the perpendicular distance and some tunable constants. And then you also have to create a torque. So depending on which side the force lies and the direction, you can have a torque that goes to the left or to the right. Clockwise or counterclockwise. So torque is basically a force that causes something to rotate, while a regular force just pushes it in a certain direction. So if you have a force that is not on the center, there's a chance that it will also create a torque. And the rules, like it's the same. Like we had, like a force can be translated into acceleration and then into a velocity and into a position. It's the same with the torque. The torque turns into an angular acceleration and then into an angular velocity and then an actual change in angle. So once you have the force of the engine, there are other forces that are at play. For example, drag. So that means if let's say you're a force and you're pushing a boat, and that is in the water, of course the water will push back. Like it's not like going to be effortless if you push it. So that means there's drag, and typical for a boat is that if you push it in length direction, it's going to be way easier than in sideways because you just have to push much more water. And drag is simply a force that is always in the opposite direction as the velocity. So in whatever direction you push it, the drag force is going to be in the opposite direction. So it's always the velocity squared with some tunable constant. And that constant is then depending on the direction. It's kind of defined by the shape of the object, and it's all simplified into a single number. So of course, the higher the constant, the more the drag. So that means if you push the boat, let's say the boat is being pushed in this direction, you're going to split this in a force in this direction and then a force in the vertical direction, and you're just going to create two drags with a different constant. That basically tells you that if you push the boat in this direction, it's easier than the other way. And then the remaining things that were done is, and that's a simplification of reality, you just orient the boat according to the surface underneath, so it follows the waves. With the height, I did a simple thing, like I assume that the boat will always be pushed up by the water, but if you need to fall down, like because the boat is moving and the surface is irregular, it's not flat, so it will go up with the waves, but it will not go down with the waves. It will go down. The rate at which it goes down will be limited by the gravity, and that's what gives you a really cool effect. If you're going faster, you'll see that you're flying more and skipping the waves, and that gives a lot of satisfaction in playing. So you'll probably see that it's all a little bit like, okay, yeah, you try a little bit, then you see if it works. So not everything is accurate. Like, for example, following the height of the waves, normally there will probably also be a drag when the boat is pushed up by a wave, and then you're not going to follow as fast, and maybe if you go too fast, you could go into a wave or whatever in real life. This was all left outside of consideration. So physics, it's always a model. If you implement it, it's a model of reality, and you can take it as far as you like it, but usually you don't have to take it too far. With a couple simple forces, like here, you can already get to a nice effect. So this was like a little bit of a one-on-one on physics and games, and it also shows how you can deviate from realistic, and this is what's important to know when you're doing physics in VR. because it's not about, yeah, go ahead.
When do you stop rolling games? When do you feel it's good enough?
Yeah, in this case, well, I was working at a game development company, and they were working with a publisher, and it's kind of like when the publisher says it's good enough. But in terms of the physics, well, you get the gameplay right, and there's kind of a general consensus that yeah, it feels good. And then stopping working on the game wasn't really like defined by the experience of the physics. It was really like, okay, now they had a whole team of testers test the game and do all crazy things like removing the disc while you're playing, and then a certain message need to appear according to Nintendo's manuals. So it was really all about the bugs and getting the critical bugs out of it. And so and that's a part of the process that I don't enjoy as much. Like it's like you come in every day as a programmer and you open up your bug tracking system and you take a bug from the top and you fix it. And meanwhile, they're actually adding more bugs at the bottom of the list. So it's kind of a never-ending thing sometimes where you make a release kind of date, and then the publisher tests it again and they say, is it good enough or not? No, okay, then you do a second release kind of date. And in some cases we did like 9 or something, and it's kind of a drag. But okay, so virtual reality and physics. So if you would do everything hyper realistic in terms of physics in VR, you would notice that you could get sick, or there could be certain side effects. And of course, there's also a limitation to how much time you want to spend implementing something and processing power and such. But I think in VR and in any game, unless you're doing like a simulation that is for whatever, where, like for an engineering firm, or I don't know, where it needs to be like super accurate or something, or if it's for product development. But if it's about a fun and engaging user experience, I think it's not about getting to realistic physics. It's about getting to what I would call natural physics. So it kind of feels natural. So it kind of gives people a feeling that they're using a powerboat. And they're having a great time, and maybe in real life it's not as fun, or it's more tricky to learn it. So you just want it to be enjoyable, so that's important in VR. So well, one of the reasons why physics in VR are awesome is because, well, of course you see it all in the first person, and what I like a lot is that you can really manipulate the world but you're using your hands once you add in hand tracking. And that's what makes it really interesting. I think it's a much more intimate way of interacting with physics. Because, yeah, it's different than there's like an extra layer of abstraction, such as using a mouse to control something that then controls an object. No, you're actually very intimately like controlling the environment or interacting with the environment. I'm just going to show a couple of examples. I think you all know VR, so maybe this goes a little bit, that's a bit too simple, but you just see that, okay, you have, you're just using your hands, and it's really, go ahead.
Were there lessons that you learned from building games for Wii that applied to the kinds of interactions with the sort of hand controllers in VR?
Well, of course, if just for myself, like as a programmer, you evolve and you learn more, and so the things I learned were really about like programming in 3D, and of course, this was because I was programming 3D games, and that's of course applicable in VR. The physics, it's similar. Like, I mean, in a way, VR is like it's kind of a different monitor, to say it really maybe a little bit disrespectful. Of course, in terms of what it can do, and it feels really different. But technically, it's a lot of the lessons from regular programming, and especially programming in 3D, can be applied to VR. Okay. Well, these are some demos that you probably played, or some people will have played if you ever touched the Vive. So this just shows how it feels really intimate, like you're controlling, you're like kind of in direct control. So this is basically what I already said. VR plus hand tracking, you get natural controls that you can't achieve with mouse and gamepad. Like if you want to like hold a bow and like accurately aim it and then maybe even change the direction of the arrow and how far you pull it, that's kind of hard to do with a keyboard and a mouse. Like you could get, maybe it would just be simplified as, okay, you click the mouse button and it will pull, and however, how long you hold it, will shoot further, but the aiming will be like super accurate, or like, I mean, well, in real life it's just really different. Like you have the stereoscopic vision, which is awesome. So you really feel like you're doing something, and it's actually much more difficult in some cases. So this is an example of a prototype we did in which you're also coincidentally navigating a boat, but it's with an oar. I'm just going to show it and I'm going to comment on it. So basically you have the oar, and you can give this to anybody. Like if you give somebody new to VR, a VR headset and the controllers, and you say, okay, to grab something, press a button. That's kind of it. That's all you need to know. So you just, you just pick up the oar and you start using the boat. So I mean, it's like simple as a user experience. It's so simple that it's really like you give somebody an oar and a boat in real life. Like figure out what to do with it. I mean, and that's what I really like. That's something that this kind of experience would be near impossible. Some things are, of course, this is where we again deviate from realism. You don't want to jump in the water because you will realize that it's a concrete floor. So we respawn it. And here, like we automatically dock the boat. So there are some things that you can learn from other games where you can deviate from realism.
One of like the hardest things I think is like you're pushing up against something, right? You expect a force back. So you experiment with any ways to like either visually trick that kind of experience.
Exactly. So well, in this project, no. I might, but I don't care.
There it is.
It's a very valid question. Like in this case, we did 2 iterations. This is what we had in the second iteration. So the first, what is really important in VR is if you look at your hands, that they are actually at that position. You cannot like say, okay, I'm going to grab an oar and I'm going to push against the wall, and my hands are like going to stay behind because they're not allowed to push the oar into the wall. So that doesn't work. So initially we just said, okay, we'll just push into the wall and we'll apply the forces and it will kind of look like it goes inside. And then, but then once we tried it, it felt like, okay, everything feels like it's paper or something, or like it feels like the walls aren't solid, which is like kind of breaking the immersion. So that was a problem. Another problem was that when we had people test it, they were picking up the oar and they were just looking like this, and they were trying to row, and they were like wiggling the boat because the oar was actually still in the water and they were just stirring the water, and you wouldn't know because you didn't have any feedback. So that's one of the changes we made. Like for that, we just turned on the vibration of the controllers. So if you're in the water, it will. Anytime it's underwater, you will feel a sort of vibration in the controller, and then you immediately know, okay, I'm in the water, or I already lifted it high enough, because if you want to paddle really fast, maybe you want to just stay really close to the water surface, and I mean, like smaller circles or whatever. So, and then the problem with the oar going through the wall was resolved by kind of attaching the oar using springs to your hands. So if you're pushing the wall, and I will play it again so you'll see it. The oar will actually slide in your hands. Or if you're hitting like the side of the boat, like I'm holding it like this, and let's say the oar goes like that, and I go down, and the oar will just stay, and my hand will just go back, and if I go up again, it will follow again. So that's how we did that. It's not like we invented that or anything. We looked at a lot of examples. Like there was this game, I think it's called Hot Dogs, Horseshoes, and Hand Grenades. And that's where you just fool around with all kinds of objects, and that's the thing they did in that game. So you see when you pick it up, in the beginning we were actually testing, because initially you could go in the boat with the oar and
Can you step back?
Oh yeah, sure. And I can turn it a bit.
Oh, I see. No, you don't have to turn it.
So you see that the hand goes outside of the original position. You see here also, like if you're touching the ball.
And then you said you engaged haptics, you engage the vibration motors
Whenever
contacts water.
Exactly. Whenever the the point where we apply it, where that we take for the force, which is I think somewhere in the middle of the pedal, and whenever that is underwater, that would rumble. So there of course it's important that when it rumbles, there's actually also an effect. So that needs to be the same position, like if and that is taken into account for whether or not that the force would be applied. So the rowing. So you have force generated by the oar, so you're rowing. So it's kind of the same as what we had with the engine of the speedboat. So you have a force at the position of the oar opposite to the which is going to move you opposite to the direction that you're pushing. Yeah, if you move like this, you're going to go forward. And that, of course, is going to apply a force to the center of the boat and a rotation, like a torque. So if you're rowing on this side, you will turn to the left. If you're on the other side, you'll turn to the right. And actually, knowing that this is the case, we even tried a much more simple and almost dumb solution in the first iteration, where we just said, okay, let's just try to fool the user, and then if you see that you're rolling on the right, we'll just push the boat forward and give like a certain constant torque to the left. If you're rowing on the other side, we push the boat, give the torque to the right. And we said, okay, that's going to be enough, but it wasn't. Like, it didn't feel like you had any control over the situation. And the same if you push against the wall, but I think it's actually in the next slide. So yeah, this just shows it. So let's say you're moving from here to here. In this case, we just apply force in that direction. So an important thing is, if you have a boat, if you're in a boat and you just put your oar in the water while you're moving, it's going to slow you down. And even though there's no movement relative to the boat, so that simply means that you have to take the positions and the world coordinates into account and not relative to the boat. So if you just look at where the position of the oar is in the water at a certain frame and then the next frame, and you just look at the difference between these two, and that applies the force and the torque in your boat. So that means you get this effect that seems to be like something you might need to implement separately. It's actually just included. And that's the cool thing about physics. If you just think about the forces, you get to situations that you wouldn't think of, things that you can actually do in the simulation that you didn't think of. I think this is kind of the same point. It just shows that if this is the first position, this is the second position, so you're not moving your oar, you're going to slow down, and because the force is going to be in the other way. While in the previous slide, you're actually going forward, your position is here, and then you move it there, so you're going to move in this direction. So there are some extra things that we didn't do, but that you could still do. Like if you're, of course, if you're rowing, the way you put the oar, if you have, let's say your oar is here in the water and then it's here, the next frame, it's going to matter whether the oar is, or the blade or whatever it's called is like this in the water or the other way, because the surface is much smaller. So if you want to take that into account, you can just look at the movement direction and the angle. If the angle versus of the oar, of the blade, versus the movement direction is 90 degrees, you have the maximum. Otherwise, you just use a cosine with the angle or something to reduce it. And then, of course, we had to ignore the movement of the oar when it's inside of the boat, because then you're just paddling in the air. You're not supposed to be able to move your boat like that. Also, when you're hitting the boat, Initially we had it so if you hit the boat from the side, you're actually pushing the boat, which is impossible if you're standing inside of it, because otherwise you fall out of the boat. Anyway, so interaction between ore and environments. This just shows the part if you hit the wall and you push back. Sometimes you're a little clumsy in VR with your big hands that only have one action. So if you push the wall, you are pushing, but there's a reaction from the wall that the wall pushes back. Otherwise, your ore will go into the wall, which is not expected when the wall is solid, of course. So basically, an interesting thing that we had there is that if you're pushing a wall, there's actually a reaction force where you stand that actually also keeps you in place. So if you're pushing the wall, it's important that you apply, let's say I'm in the boat, the wall is here, I push it, so the boat has to move in this direction. You have to do that in the position where you stand. Because let's say if you're standing, and maybe this will be intuitively understandable, like if you're past the center of the boat and you push the boat is actually going to move like this, while if you're standing at the back, it's going to be the other way around. So that's why you have to apply the force on that position, and then you just have the old story again. You have your force translated into the force in the center of your boat with a torque in either direction. The importance of haptic feedback we already discussed. Go ahead.
So to determine the strength of the opposite force when you're pushing against the wall, is that like a constant force back on you, or do you like multiply that by the speed that the user is?
Yeah. So what we did is you just look at the difference between, well, because you have your frames. So if let's say a frame takes 90th of a second, ideally, if you have 90 frames per second. So you just look what is the position now and what is the position in the previous frame. Of course, the next frame you don't know because it didn't happen yet. And then you just look at the distance between the two, and then you just, in our case, you just multiply it with a factor. And then you tweak the factor until it feels all right. Yeah.
Did you have to do any smoothing, or could you just do straight one position, next position, and that's it?
Yes, that's it. So where I'm saying frame, I'm not actually being accurate. There's a physics update. So because ideally, to have a smooth experience visually, you just want the highest frame rate that you can. Well, maybe cap that, whatever the monitor is able to do. But for physics, you want a constant frame rate, like a constant rate. In Unity, it's called, like, you have the physics update, and you can decide how many updates a second. So usually it's higher than a frame rate. The higher, the more accurate your physics will be. So if you consider a certain curve, and you have smaller intervals, so you'll have smaller line segments added to the curve. So it will be closer to the real curve. Well, if it's bigger, you'll probably overshoot. Like if you have a curve that goes like this, the line segments are going to go too far, and your curve will end up higher. Which actually doesn't matter because you can just tweak your parameters and bring it down again until it feels all right. But higher, it's typically better if it's higher than your frame rate. You don't want objects to not move for a frame, because then it will feel like it's like stuttering. Yeah.
Right.
So that way, if you have, like, let's say you have 50, let's say you have 100 physics updates per second, and the frame rate varies between 30 and 90. That means sometimes it will do, like, maybe if it's 30, it will do like 3 updates for one frame, and then maybe if it's 90, it will do 1, and sometimes 2. Yeah. So importance of haptic feedback, we mentioned, so that was about that you have to feel whether you're in the water. And also when you're hitting the boat, there was like an effect. So it feels more like the boat is actually present. Otherwise it just feels like it's not there. It's the same with, like, pushing it, or just straight through a wall. It just feels like the wall isn't there. It's kind of like a ghost. So I think it's important again, like to deviate from realism whenever needed. I'm just thinking of where we deviated from realism. Probably about everywhere, but yeah. I think one of the major deviations from realism when doing games or just experiences that need to feel good, and it's not like a engineering kind of simulation, that the most important deviation is that you just put constants everywhere and then you tweak them until it feels good. Like you have different forces, like so you have, let's say you have your oar pushing the boat forward, you have drag forces, and you just tweak all the constants until it feels right, and that it's basically based on previous experience playing with the boat.
Yeah, I just wanted to ask, where are the places where it's totally fine to deviate from realism as much as you want, and things are gonna feel weird or get sick, and where are the places where you absolutely can't really touch, or else you sort of ruin the art?
I think the most important thing is when we're talking about the constants, that's just something you tweak until it feels good. So that's not really an issue. But if you omit certain forces, then it's just not going to feel like real. Sometimes you just have to think what is the real situation, and what forces are at play in real life, and then you have to you just add more and more of these, and it's really based on how big you think the forces are. Some things are really tiny. For example, there's also drag with the air. And maybe that would be significant if there's a lot of wind. But that's totally ignored. There's no. We didn't use any of that. And by the way, if that would actually be combined into the air plus water, assuming that. Well, that's not exactly true. So it depends on the speed of the water versus the boat and the air versus the boat. But you can intuitively know that drag with air is not going to be as heavy for a boat as drag with water, for example. So if you drop too many of these forces, the initial approach was really let's just ignore physics, kind of, and we'll just push the boat a little forward and turn a little bit to one side or turn to the other side, depending on where we detect that you're rowing. That, for example, didn't work. And then we really had to say, okay, we have to really make it more realistic. We have to take the actual position of the oar in the water into account, which, by the way, just by applying the simple rule where you take your force outside, you put it to the center. So the amount of torque is also going to depend on how far your oar is. So if you're rowing further out, you're going to turn way more than if you're rowing closer. And that's and you get that for free, basically, all those effects. I hope that covers your question. I mean, for free, as in you just implement it as a simple system, you determine the force at a certain place, you apply it, and before you, maybe sometimes without realizing, you notice, this actually makes a difference if I row nearby or further out. Oh, this is the example of deviating from realism, yeah. This is about docking. You don't want to be docking at exactly the way the game expects you to dock. Let's say something would be triggered in the game which is dependent on whether you're docking a certain area. So certain area means there's going to be a threshold. You're either docked or not. And that could be tricky in a game because it could be just a little bit outside of that area, and then there's no way to intuitively feel whether you're there or not, and you don't want to be. Basically, you want to skip the boring parts. So what we did is you had a certain radius or a certain area, and where you want it to be if you're officially docked according to the game, and then there's a wider area around it. As soon as you're in that wider area, it will gently push you towards that place. And then once you're there, it will actually kind of disable the wider area, so you can actually leave, otherwise you would kind of be stuck there. That's an example where you deviate from realism. Dealing with nausea, I think the most important thing here is that what is not realistic in terms of the experience is that you're holding very light controllers and you might be wielding a heavy object, heavy object. And some developers say, okay, we want to keep the experience like realistic or like true to the real life experience. And then they would say, okay, you cannot move around in VR. You have to teleport because you don't actually physically move around. So that creates a certain level of discomfort. Also, some developers, like the guys from Alchemy Labs that did like Job Simulator, said like, okay, we only manipulate objects that are about the same weight as the controllers. So you have like a stapler or a mug, like all small things. You're not going to hold like a rock because it will feel like it's big. So that's also one of the issues here. Like you're holding an ore, but you don't really feel the actual mass. That also means that you can like move the ore in a way that you wouldn't be able to do in real life. You can like move it really fast, or like hold your hands really close and like this, and you will get like extreme angles and very fast movements. Which in real life you can hold like a heavy object like this and then be flapping it around unless you have superpowers. So how to deal with nausea? Just avoid it. Avoid nausea-provoking situations. The most simple way would be to say that the boat cannot move. But that would be boring, like you have no oar and you just stand in the boat. Then you wouldn't get nauseated. Of course, this ties into what I was saying about because the controls are really light, you can make movements, you can move this oar in a way that you couldn't in real life, like you can make like small movements and the oar will be like making extreme angles very fast. So that would mean, if you didn't do anything without intervention, it would mean that the boat would go crazy fast. And then you get sick instantly because you have insane acceleration. So we just limited it. So, and usually if you limit something, you don't want it to be like a hard limit, you want it to be like, to attenuate, like you will maybe at a certain amount of motion, there will be certain force, and then the extra motion will just be taken into account less and less and less until it kind of tapers off. That's a way that you can make it so you don't really feel that you're not going faster, that the effect is there, but it actually really prevents you from being nauseated. This is another example. This is a forklift that I was talking about. This was for a company in New York. They're doing, it's called Next Day Safety. They do all kinds of safety things in VR. So here you're in a forklift, you're actually sitting on a chair. You could stand, but then maybe you can't reach the steering wheel. So yeah, you have the controls. Like here also there's no haptics, but we just highlight the objects in an obvious way. Like if you're touching the steering wheel, it becomes yellow and such. So you have all the forks, you have these what looks like stick shifts on the right. But this is like to make it go up and move the fork forward and backwards and then angle it. So you have to take a pallet and then you have to angle it, because if you just take a pallet, you lift it up, you drive backwards, it's probably going to drop. You have to angle it a little bit upwards so gravity helps it stay. So this was about having this as a module for people that are learning how to use a forklift. In a way that it makes them aware of their surroundings. So it creates a surrounding with a lot of risky situations, like people cleaning and that can't hear you because it's too loud. You have overhanging wires. And a ramp, and you have to pick something up. You don't want to drive with a pallet in front of your face where you can't see anybody. But if you put it too high, you need to know is there space? Isn't there an obstacle? One example that you did in this case to prevent nausea from setting in too much is, one of the things in VR is if you have a rotation that you don't experience in real life. Let's say you're sitting in a chair and you're turning to the left and you're driving really fast, like you're turning in VR and not in real life. That's one of the things that really makes you nauseated more than just moving forward while you're not moving forward in real life. So that the trick by just reducing the acceleration. It's like your gas pedal is less effective while you're turning, as opposed to when you're just driving forward. We're almost there. Conclusions. I can't see my presenter notes, so I don't know anymore. Here. So implementing physics is a lot of fun because you're experimenting with a system. It's kind of like a sandbox. We talked about natural versus realistic experience. It's not about, in most cases, the optimal experience is not hyper-realistic. It's about creating something that feels natural. So where you're actually deliberately deviating from realism to get to a better experience, to make the user feel in control, to make it actually a little bit easier. And then avoiding nausea when you can, like if you can avoid locomotion at all. But of course, if it's about like people practicing driving a forklift, you cannot avoid that. But you have to be careful with like rotations and such. And then also showing the hands where they actually are is like super important. Otherwise, you get a kind of out of body experience.